All right, so in chapter 7, section 4, we're going to be talking about functions and their inverses. So we did inverses way back in chapter 5, section 1. And we want to expand those ideas to what we're doing in this section. So let's take a look at some of our functions. So let's start with graphing sine x on negative pi to pi. So if we were to graph our sine function, we know that sine of 0 was 0, and sine of pi over 2 was 1, and sine of pi comes back to 0. Sine of negative pi over 2 was negative 1 back here. So our sine function is a wave that looks something like this. If we were to look at the sine function from negative pi to pi, is this function 1 to 1? And the answer is no. So in order to make the sine function 1 to 1, to make the sine function 1 to 1, we must restrict its domain to negative pi over 2 to positive pi over 2. So basically what we're going to do is if we chop off the sine function here and the sine function here, so here and here, and imagine getting rid of everything that's out here. If we do that, this new function is 1 to 1. That is, it passes the horizontal line test. So with the restricted domain, sine is 1 to 1 and has an inverse. So if we think back to chapter 5, section 1, to find the inverse, we interchange all of our x's and our y's. So then all of our y's become x's and all of our x's become y's. So then we would get something that looks like this-ish. So we have our inverse. So the first thing that we notice when we do this is for our sine then, it would have domain from negative pi over 2 to pi over 2, and its range would be from negative 1 to positive 1. Well, that makes the domain of the inverse sine from negative 1 to positive 1, and its range from negative pi over 2 to pi over 2, because we interchanged all of the x's and y's. We did something very similar to this in Chapter 5 when we defined the exponential function and then defined its inverse, the logarithm in terms of the exponential. We're doing exactly that same construction here. But the issue that we're running into is since these functions aren't one-to-one, we had to chop them up because the domain of the original sine function goes on forever in both directions. But that function doesn't have an inverse. So when we do this, we have to cut things up just a little bit to make things work the way they are supposed to. So let's go ahead and talk a little bit about our inverse trigonometric functions. So the inverse of f of x equals sine x is, and that's our notation for the inverse, f inverse of x is equal to the sine inverse of x. So once again, we have to be a little bit careful. So warning, the negative 1 is not an exponent. So sine inverse of x does not equal 1 over sine x, which would be the cosecant of x. So for trigonometric functions, when we're writing the inverse, we put a negative 1 where we would normally put an exponent. But we know it's not a negative exponent, it means 1 over, because if we want to write 1 over sine, we don't write 1 over sine, we write cosecant. We have a function for that already. So the symbol is read as the inverse sine of x or sine inverse of x or, if you go old school, the arc sine of x. So the arc sine was used historically when the printing press was still really young. It was hard for them to make things like exponents, so they typed out arc sine or put arc in front of functions to designate their inverse. So when we say arc sine, it's really just a different way to say inverse sine. All right, so before we do the next example, let's remind us of something. So when we have the sine function, so if I have y equals sine theta. My input is an angle, and my output is the ratio of the sides of a right triangle. So then if I have the inverse function, y equals the inverse sine of x, well, that means I interchanged my x's and my y's, or I interchanged my inputs and my outputs. So for the inverse sine, my input would be the ratio of the side, or of the sides of a right triangle, and my output would be an angle. So remember, with trig functions, we put in angles and we get out the ratios of the sides of a triangle. So inverse trigonometric functions have to undo that or do the opposite of that. So that means we're going to put in the ratios of the sides of a right triangle, and the inverse trigonometric function is going to give us back an angle. All right. So let's take a look at example number 2, but let's zoom in a little bit. Example number 2. Says find the exact value of the sine inverse of square root of 2 over 2. So based on what we just wrote above, the sine inverse asks the question, what angle in negative pi over 2 to pi over 2 has sine theta equals square root of 2 over 2. So the inverse trig function is asking us what angle in between negative pi over 2 and pi over 2 is equal to, whose sine is equal to root 2 over 2. All right, so if we're only looking at angles between negative pi over 2 and positive pi over 2, then that means we are only looking in quadrants 1 and 4. So that means we're looking at the right half of the unit circle. So if we're looking at the right half of the unit circle here, sine is the y-coordinate, so we know that sine theta equals y. So if sine theta equals y, we're looking for a y value that equals root 2 over 2. And that's going to happen right here. So what is our corresponding angle? Pi over 4. So the sine inverse of square root of 2 over 2 is equal to positive pi over 4. Because the sine of pi over 4 is square root of 2 over 2. All right, let's take a look at our next example. So example 3 says, find the exact value of cosine inverse of negative 0.2689. So, grab our graphing device. Let's put our y equals in. And we're going to graph cosine x. And we want to know, well, when does cosine x equal negative 0.2689? And let's go ahead and change our window. And let's just go from negative 2 pi to positive 2 pi. And then let's make our x-min -1 and our x-max +1 and scale in 0.1s. And we go graph. And we get something that looks like this. And we know that each time those curves intersect, we're going to get a solution. So the first thing we notice, at least on this screen, I can see several different solutions. So I have a solution here, 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 and here. On my calculator. But now, let's go back to our home screen. What if I just ask my calculator? So we want to take note, we have sine, cosine, and tangent. If we look at the second functions on our calculator, we have sine inverse, cosine inverse, and tangent inverse. So if we go second cosine, and we put in negative 0.2689, hit enter, we get this value. Well, that only gives us one solution. In fact, this solution is this solution on our graph. And we know that we're going to pick up other solutions as we wrap around the unit circle. And we're going to talk about those. So the first thing that I want to emphasize about this is when we use our calculator to get the inverse of any trigonometric function, it's only going to return one solution. We're going to talk about which solution it returns and what range that's going to be in. We already know for the sine function, because of how we had to restrict the domain, that it will only give us answers between negative pi over 2 and positive pi over 2. But it is unique to each trigonometric function. So, if we recall that for inverses we have the following. If a function is truly invertible, then f of f inverse of x equals x, and f inverse of f of x equals x. But since sine and cosine are not one-to-one, we have the following restrictions. So the first one that we need to take note of is that the sine of sine inverse of x is equal to x for all x in the domain of sine inverse. And the domain of sine inverse, as we saw above, it's for all x between -1 and 1. So to be explicit then, the sine of sine inverse of 0.5, since 0.5 is in between -1 and 1, the sine and the sine inverse reduce out, and we get just 0.5. And we can check that on our calculator. So if we go sine of the sine inverse of 0.5, our calculator will agree that we get 0.5. But if I had something, for instance, sine of the sine inverse of 2, we might erroneously believe, oh, sine and sine inverse cancel and we get 2. But if I try that on my calculator, it's going to tell me error domain. And this is because this is not equal to 2. 2 is not in the domain. So we can't just get overly simple about this and cancel them out. Since they're not one-to-one functions, we have to be careful and only do it if things are in valid domains. So we have something similar for cosine. So for cosine, we have that the cosine of the cosine inverse of x is equal to x for x in -1 to 1, so the same thing. For tangent, the tangent of the tangent inverse of x equals x for all real numbers. So there's going to be no restriction. If we switch the order, so notice with all of these, we were taking the sine of sine inverse, the cosine of the cosine inverse, and the tangent of the tangent inverse. Well, what if we switch the order? So if we have the sine inverse of the sine of x, this is equal to x for x in -pi/2 to pi/2. For cosine, the cosine inverse of the cosine of x is equal to x for x in 0 to pi. And lastly, for tangent, the tangent inverse of the tangent of x is equal to x for x in -pi/2 to +pi/2. All right, so let's go ahead and take a look at our next couple of examples. All right, so for the first one, we have tangent inverse of the tangent of pi/6. So tangent inverse of tangent of x is equal to x as long as x is in between -pi/2 and pi/2. So pi/6 is in, so pi/6 is in negative pi over 2 to pi over 2. So then those two cancel, and the answer is just pi over 6. All right, so next one is for you guys, so let's go ahead and do that. So we check for cosine inverse of cosine, the input needs to be between 0 and pi. Well, pi over 2 is, so these two guys reduce out, and we get just pi over 2. We take a look at our last one, which is the sine inverse of the sine of 3 pi over 4. So sine inverse of sine equals x if x is between negative pi over 2 and pi over 2. Well, 3 pi over 4 is bigger than pi over 2. So this is not in negative pi over 2 to pi over 2. So let's check on our calculator and see what we get. So if we go sine inverse of the sine of 3 pi over 4, we get this, but if we check, is that the same as 3 pi divided by 4? And the answer is no. So that's interesting. So we see that they're not the same. So this does not equal 3 pi over 4, as we just saw on our calculator. But it did give us some value, right? So let's see if we can figure out what that value is and why we got what we got. So to help us with that, we're going to turn to the unit circle. So with the sine, we go between negative pi over 2 and positive pi over 2. So that's the right side of our unit circle. But when I look at the right side of my unit circle, we first notice why we have the problem. 3 pi over 4 is not in the right side of this unit circle. So when we go back and look at our unit circle, where is 3 pi over 4? Well, 3 pi over 4 is actually in quadrant number 2 over here. So 3 pi over 4 but it is in So if we take a look at 3 pi over 4, that's here. So what's the sine of 3 pi over 4? Well, sine is y. That's pi, or root 2 over 2. We'll notice that if we come back to where we're supposed to be in quadrants 1 and 4, we also have a square root of 2 over 2, which pairs up with pi over 4. And if I grab my calculator and check pi divided by 4, and I compare that with what my calculator gave me, it gives me the same answer. So what's happening is, since the range of the inverse sine function is negative pi over 2, even though the answer that it wanted to give, or that we thought we should get, was 3 pi over 4, it translated that angle into a sine function that has output root 2 over 2, but whose angle was in the appropriate range, which was negative pi over 2 and pi over 2, which is pi over 4 here. So that's why we have to be careful, is that if we're not, we'll get answers. They just won't be the correct ones, or the ones that we are looking for. All right, so let's take a look at our next example. So example 5, write the trigonometric expression as an algebraic expression. So we have the sine of the tangent inverse of x over 3. So if we let theta equal the tangent inverse of x over 3, by definition, tangent is opposite over adjacent. So this would be my opposite. And this would be my adjacent. So if that's the case, the opposite of theta is going to be x, and adjacent to theta is going to be 3. The next thing we were asked to do, part B, is use the Pythagorean theorem to find the missing side of the triangle. So if that's the case, we have 3 squared plus x squared is equal to c squared. So then that gives us 9 plus x squared equals c squared. So then c is equal to the square root of 9 plus x squared. So that means the hypotenuse of this triangle is 9 plus x squared. So then the last part of our problem is use the definition of sine to find the exact value of sine of tangent inverse of x over 3. So now sine, by definition, if this is our angle right here, so sine by definition is opposite over hypotenuse. So then our opposite is x, and our hypotenuse is the square root of 9 plus x squared. So then that gives us that the sine of the tangent inverse of x over 3 reduces to x over the square root of 9 plus x squared. So we can use this technique to simplify when we have inverse trigonometric functions inside trig functions where they're not exactly the same. When they are exactly the same, if we have cosine of cosine inverse, we know that under certain circumstances we can just reduce them out. But when we have a mixture, the technique that we need to use is we create a triangle, solve for the missing side, and then use that triangle and the definition of the trig function to find what it is we are looking for. All right, let's take a look at our next example. So this one is asking us to do exactly the same thing. It just didn't scaffold out all of the steps. So we look at our inside function, and we have cotangent. So cotangent is adjacent over opposite. So I'm going to do u and make it into a fraction over 1. So then this is going to be adjacent. And then this is going to be opposite. So if we draw our triangle, our adjacent is u, and our opposite is 1. So then we have u squared plus 1 squared equals c squared. So c squared equals u squared plus 1. So c is the square root of u squared plus 1. So the hypotenuse then is u squared plus 1. So then we want the sine of that. So when we take the sine is opposite over hypotenuse. We get 1 over the square root of u squared plus 1. All right, let's take a look at example number 7. We want to simplify the same thing, and once again we see the cosine inverse of 1/2, and we know that's an angle, but we have 2 times that angle. So we want to remember that inverse trig functions are angles. So if that's the case, we need to use the double angle identity, because we have the sine of 2 times theta, where theta is the cosine inverse of 1/2. So by the double angle identity, we have that the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. Well, in our case, we have our theta is the inverse cosine of 1/2. So that's 2 times the sine of the inverse cosine of 1/2 times the cosine of the inverse cosine of 1/2. And now this is just like the problems we were doing before. So we have our cosine, and by definition, cosine is adjacent over hypotenuse, so that's a 1, 2, and we solve for the missing side, which I'll call x, so 1 squared plus x squared equals 2 squared, so 1 plus x squared equals 4, minus 1, we get x squared equals 3, so then x is the square root of 3. So now we want to find the sine of this angle. So it's going to be 2. The sine is opposite over hypotenuse. So that's root 3 over 2. And the cosine is adjacent over hypotenuse. Or notice they just cancel out. Either way, we get 1 over 2. Those reduce out, and we get the square root of 3 over 2. So the sine of 2 times the cosine inverse of 1/2 is square root of 3 over 2. All right, so we don't have a ton of time left, but the last one is for you guys to finish up as a you try. So let's go ahead and simplify up. 2 times the sine inverse of root 2 over 2. So to resolve this, we have a double angle again on sine. So if we draw our triangle, sine is opposite over hypotenuse. So that's going to be root 2 and 2. I'll call this x. So then I have x squared plus the square root of 2 squared is equal to 2 squared. So that's x squared plus 2 equals 4. Minus 2 minus 2, x squared equals 2. So that gives us x equals the square root of 2. So then we have a square root of 2, square root of 2, 2 triangle. And we go look on our identity sheet for our tangent double angle identity, which is going to be this guy right here. So then we're going to get 2 times the tangent, which is going to be square root of 2, because tangent is opposite over adjacent. So square root of 2 over square root of 2 is going to be just 1. So 2 times 1 all over 1 minus 1 squared gives us 2 over 0. So that tells us this is undefined because it's not in the domain. And if we recognize this, the tangent, or the inverse tangent of root 2 over 2, or root 2 over root 2 is 1, and tangent is equal to 1 at pi over 4. And twice pi over 4 is pi over 2, which isn't in the domain of tangent.